Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth.
Hello, folks. On today's episode, we discuss a momentous Martian milestone, propulsion, the ASCENT green propellant, and how to throw yourself at the ground and miss. Douglas Adams' Secret to Flight.
In 3, 2, 1.
Today we're joined by Corinne Sedano. She's a group lead for Chemical Propulsion flight systems in our propulsion division. Corinne, thank you for joining us.
Oh, thank you, Ken. It's a pleasure to be here today.
So first question for you, something I've been wanting to ask the right person for some time, is I'm a huge fan of The Hitchhiker's Guide to the Galaxy. And there's a really famous quote from it. They say flying is like throwing yourself at the ground and missing. Is there any truth to that, propulsion, or what you do?
Yeah, a little bit. So when you think about spacecraft in orbit, they basically have enough energy that they're always trying to fall toward the Earth, but missing because they just have enough orbital energy to stay in orbit. So if you translate that to thinking about just throwing a baseball, you're putting only so much energy into that baseball. And so it's going to eventually make an arc, but it's going to fall to the ground. And then if you translate that then to, let's talk about suborbital things such as missiles, they have a little bit more energy. And so they're able to go at a much higher altitude, but they're still not going to quite reach orbit, but they can go very far across the Earth and then still land. But then by the time you get to launch vehicles and spacecraft, now you've put enough energy into that vehicle that it'll actually reach orbit. And that energy is sufficient such that it's actually never going to hit. It always wants to try to hit the ground, but never can. So kind of trying to use that baseball analogy there. But think about just putting enough energy into a baseball that eventually it's just going to go around the Earth.
That's fascinating. So it looks like I always thought that when I read that, it seemed kind of silly. I'm like, I don't know if Douglas Adams did his research, but it sounds like, it's not all wrong.
No, not at all.
So I want to take a step back then, now that we have a really good analogy in place, and talk about where did your interest in propulsion in space originally come from?
Sure. It goes all back to middle school, actually. And two major things happened in the middle school time frame. Actually, both kind of in 1997. Both of those were key, as well as a astronomy elective I took in middle school. And one of my good friend's parents actually volunteered to teach that astronomy elective. And that was one of the few classes that really kicked off my interest in astronomy and thinking outward to space and the stars and exploration. But then in tandem with that, both Mars Pathfinder landed on the surface of Mars in 1997. And then the Cassini mission to Saturn launched that same year. And the neat thing about both of those were, for Pathfinder, it was the first time we've landed a robotic rover on another planet. And I remember my parents taking me to the Natural History Museum in Denver, Colorado. And there were a bunch of different interactive things you could do there and learn more about Mars and the rover and such. And that was really, really exciting. And then with Cassini, it was a totally different perspective, right? So you're going from the mission has just landed on the surface of somewhere, arrived at its destination, to something that's just launching. And oh, by the way, it won't reach its destination until you're in college, and you're sitting there in middle school thinking about it. And then, once you're in college and you say, oh my gosh, it's arrived. And then moving on into my career, working with people who are actually still working that mission, and I'm actually a professional working in space. So those are kind of the major things were that astronomy elective, and then those major space happenings as well really kicked off my interest in aerospace engineering and wanting to be an engineer.
I was just going to say how nice for some of the birds to join us today. We're really talking about aerospace engineering. They want to tell us what's up. I'm not sure if they could really explain propulsion to us though. So if you could give, some, non-rocket scientists, non-chemists, non-aerospace engineers, what's Propulsion 101?
Sure. So Propulsion 101 for this case is basically saying what I do on a day-to-day basis kind of is actually I'm very fortunate working on either developing or testing thrusters. And in my case, I specifically focus on an area that's for spacecraft, so smaller thrusters. So not thinking about launch vehicles or large engines, but smaller. And when we talk about rocket propulsion, then we're talking about basically taking a propellant and through one means or another, igniting it such that you turn it into basically a very, very hot gas and exhaust it through a nozzle to create thrust. And so kind of one of the key people to kick this off was Goddard, which we have a NASA center name for as well. And this was back at almost the turn of the century, the 1900s century, by the way, not 2000s. Those kind of things are basically what I focus on. And then the size of the things I work on from a rocket propulsion standpoint are basically no larger than kind of your average shoebox, maybe a little bit larger in terms of thruster size. So nothing momentous. And so if you were to go YouTube and look at solid rockets and some of the testing they do on the ground, acceptance testing in Utah, or for example, the recent SLS engine checks that they do out at Stennis, those are orders of magnitude larger than what we typically look at. And the reason being that for spacecraft propulsion, you're fitting into a much smaller box. So you are mass and volume constrained as far as how you approach things. And then on top of that, we can look at different propellants and different things that we put through that thruster, that rocket engine, to create different thrust classes, different performance, different basic gas mileage, if you will, how much thrust or how much performance you get per gram of propellant, if you will. So those are all key things in terms of propulsion and how we use it.
That kind of sparks a little idea in my head. So with these smaller satellites you may be working with, is part of the benefit of using those, that not only saving money, of course, but as opposed to a larger satellite, is to maybe test out new ideas with thrusters that maybe not fully vetted for a larger satellite? Like, are those used as test platforms for larger platforms, or what's the benefit?
And for the audience, a lot of the terminology that comes up is something like CubeSat, and a CubeSat would be something that's, the size of a shoebox or something of that nature. So those are, I would say, cost-effective platforms for testing things because you can launch multiple of them. They're not necessarily robust. They're probably going to go into low Earth orbit. And usually, given their size, they don't have propulsion, so they don't last all that long compared to other things you think about, like Voyager or something that's been out there since the 70s. But CubeSats have a much shorter lifespan. But yes, indeed, they do offer themselves as a great test platform, amongst other things, for not just propulsion, but for a myriad of other payloads. And in fact, for all other subsystems, really. So they're great for that. The challenge in those, though, is the packaging, of course. So while they do lend themselves to a great test platform, the engineer has to be mindful about trying to compartmentalize and densify what they're trying to do to miniaturize it, really, because most of the applications still reside, especially for propulsion, into a little bit larger, what they call the ESPA class. And the ESPA class terminology really just comes from the type of ring that these spacecraft are attached to. So it's basically a ride share, if you will. So there's a much larger spacecraft on the launch vehicle. And then a grouping of a handful of satellites will go and attach to this ring because they have a little bit extra, basically, room on board, if you will. It's trying to shove those last little boxes into your car, your trunk, right? When you're coming out of Costco and you're trying to get everything in there, same idea here. You got the big stuff, and then you got a few little things you're trying to wedge in, but you got the room. That's the same idea here. So you're trying to get all these little satellites installed. They're like the size of mini fridges, basically, compared to some of the huge satellites that you'll see in larger orbits or just more expensive satellites. And once you break into that kind of mini fridge size, then that becomes more of the commonly used propulsion. So certainly CubeSats lend themselves to testing things out. But then after that step, you really want to take it up to the next notch and look at ESPA class and then even larger, maybe like 1,000-kilogram satellites to really vet your technology, because there's still a large demand across that kind of spacecraft spectrum.
And before we even get him up there, then, I know we were still kind of talking about a lot of these cool terms that you're covering. We know there's still other testing that has to go down. So something I've always been interested in kind of getting a clarification on is we've heard the term hot fire test. What does that mean for a thruster, and why is it so important?
Sure. So hot fire is a key test that is done for basically all engines in one format or another. And then the instance in which my area focuses on it is actually in vacuum chambers. And so what we're trying to do via hot fire test is actually run the engine in a relevant environment, i.e. vacuum, so the vacuum of space, and verify the performance. And for those of you out there, go ahead and pause this real quick and go to YouTube and take a look. There's a plethora of great material out there, not just looking at small thrusters, but also for solid rockets, large liquid rockets, all of those. But we're trying to get it to as close to the vacuum of space as possible. And then we're looking at different operational scenarios for the thruster. So in certain situations like development now, we're just looking at how does the thruster perform over the course of an entire kind of operating box, putting it through its paces. It'd be like taking a car to the test track and putting it through all the different runs, right? But in this case now we're looking at, well, how does the thruster perform if we turn it on for 30 seconds straight or minutes straight or 20 minutes straight? How do all those things change? How does it behave thermally? How does the propellant behave? How does the hardware itself behave? And then those scenarios could include everything from orbital plane changes, so looking at changing your inclination. So I want to change looking at Los Angeles, California, and go start looking at the Antarctic or something like that, right? So now we need to change the inclination at which we're looking at the Earth. And then the second is just changing the actual orbital altitude. All those things play in. And then the final one is pointing. So when we look at, do we want to change the orientation of the spacecraft in its orbit, but just point at something different? Then you start looking at turning the thruster on and off in a very vigorous and rigorous cycling to give it that little bit. So you're kind of trying to throttle the engine, if you will, to get that precise pointing that you want. So all of those things go into a test of hot fire, but you're actually using the real thruster, the real propellant, but you have a large amount of instrumentation to monitor all the things that you want to understand in terms of how the thruster is performing. So either A, you can verify its performance, or B, make a better development, or do both.
So that's something I'm trying to wrap my head around. So this may sound like a silly question, but I know when you're actually in space, let's say these CubeSats or these smaller satellites, is it indeed just one thruster? Like, it sounds like with all the adjustments, are there multiple on the actual satellite itself?
Oh, absolutely. You can have everything from 4 to 8 to even more. And it really depends on what the requirements are of the mission. And for even example, the redundancy. So you might just have a dual set of thrusters just because you want to make sure that your mission finishes. So if one goes out or two go out, then you have backups. On the other hand, some satellites, to be more cost effective, will just go what we call single string and just have one set. But they may still have 8 because they want them on all corners of the box to be able to do things really quickly. So yes, more than likely you're going to have multiple engines, and you may even have multiple thrust classes on the same spacecraft. So 1 or 2 engines, for example, like a Cassini. You have engines that do some really heavy duty burns to get you into the right orbits. And then you have other engines to help control those burns, to keep your pointing and your attitude correct so you don't spin out of control, and or do the finite pointing as well. So you may need multiple tools in your thruster Swiss Army knife to get you through the mission.
That's really cool. Yeah, because I always imagined that you'd have to have multiple set up. Otherwise, how could you do those, like the fine-tuned movements? But to have that explained in a better manner, I mean, I have a much better visualization, now, which is neat. Because like you were pointing out earlier, there are so many micro adjustments to make during one mission. Like you mentioned, if you have to observe one thing, adjust your trajectory for another, like it's amazing to think about how precise everything is up there.
Very much.
And one cool part of your career, so we kind of touched on this earlier, talking about awesome missions going to other worlds, was you got to work at NASA's Jet Propulsion Laboratory. What projects did you actually work on while you were there?
Yeah, I was very fortunate to work there for over 10 years, and I worked on quite a few missions, but I like to highlight at least 4 of them. And I find myself, again, fortunate to have worked at such a great place because I was able to work on 4 different regimes of aerospace, and specifically space operations, if you will. So I was able to work on suborbital flights, which is basically kind of back to that baseball missile analogy earlier. We just came up and came back down. We never actually achieved orbit. But it's called the Low Density Supersonic Decelerator. And it was basically a development program for a different way to land larger payloads on Mars. And so we launched basically a vehicle from a weather balloon and brought it up to a pretty fast speed using a solid rocket motor, and then deploy the device. And so you can go on YouTube and look at that one. That's a fun one to watch with the parachute deployment and everything. And then for low Earth orbit, I worked on the propulsion system for a satellite called SMAP, Soil Moisture Active Passive. That was a great opportunity because that's when I really got all the hands-on knowledge of how to put together a propulsion system, not just do it on paper, but actually apply my knowledge as well. Then, as far as inner planets, I was fortunate enough to work on Mars 2020, and I was the lead integration and test engineer for the Sky Crane. So the part of the vehicle that will actually descend to the surface and cut the cord for the rover was the main area I worked with. And I worked with a great team of people putting all that together. It was not a single person effort at all. last but not least, I worked on for outer planets, so looking beyond our inner planets here. One of the last projects I was able to work on was Europa Clipper. And so that one's still down the road here to launch, but it'll be another great mission to watch as well once that launches. So I kind of like to think I've got, my 4 merit badges for different regimes of space as well. So it's a very great opportunity.
I'm trying to wrap my head around that too, because it's so cool to think that you're working on these projects that are going to be out literally on other worlds. And what is it like? Is there some sort of disconnect while you're working on it here on Earth? Obviously, you're like, okay, I'm working on this here. It's right here in front of me. It's a real physical thing, but I'm preparing this to go thousands of miles to another planet. Like, what is that like? Like, what is that headspace?
Yeah, I mean, it's one of those really neat things about going to work every day, I guess, is that you go and you always have this moment of realization every once in a while that I'm touching. I mean, you always have gloves on and things like that, so you're not really touching it. You can't leave your fingerprints on it, right? So, but you're always working around hardware that is going to another place, but it's always surreal until you kind of transfer it to the next stage of its development. So, for example, on all the programs I worked, really, as you move from the thing that you're working on and doing every day, and you're reminding yourself, oh yeah, this is going to go into space at some point, and this is really cool, and I need to kind of soak this in, and then it kind of transfers on to the next stage of integration, and so you get to see it and go visit it in the clean room or the high bay and go say hi to it and show it off to friends and things like that, and then eventually it goes to the launch site and you kind of don't see it again, and then it launches and you're like, yes, we got a great launch. And then, you'll be sitting in a meeting or something one day and you'll be thinking about, oh yeah, my spacecraft's still headed to Mars right now. This is pretty cool. And then, of course, proof is in the pudding, though. The landing tomorrow is going to be just a great thing to watch. But it's all very surreal because you are doing everything in a very much a virtual environment after launch. It's always taking data and watching video and things. So looking forward to that day, maybe, a generation or a couple generations from now, where we've got astronauts on the surface of Mars and they're actually watching some of these things land, and it's not just this virtual environment, but people are actually walking up to stuff, like the Martian, and they go find Pathfinder, that kind of thing, right? So
do you have any interest in being one of those people on Mars, or you just kind of want to do the work back here?
Oh, the work back here, I think I'm not that old, but I'm already too old to probably get my hat in the ring on that one, so I'll leave that to my children to take the hold of that one. Go move it forward.
There you go. And speaking of moving forward, how did you make the jump from JPL to then the Air Force Research Laboratory?
Sure. So as we were talking about at JPL, I worked on all these really great programs, but I was ready for the next challenge with respect to propulsion. And this great opportunity at AFRL came up to work on the maturation and development of ASCENT, formerly known as AFM315E, which is a new type of propellant, basically. So I applied for that job and it was a good fit. So kind of taken it up and started running with it. But it's been a lot of fun to work on these past couple of years. And I'm looking forward to keep moving the ball forward on the development.
So that actually is a perfect connection as well. I know we introduced you early on here as being the group lead for Chemical Propulsion flight systems. Is that still what you're working on then, things like the ASCENT propellant, or has your position changed over those years?
Within my group and my branch or my area, we look really at thruster level and above. So how do we get those thrusters basically onto spacecraft, and how do we bring this propellant onto a spacecraft? And so I certainly can't take the credit for the early work and the momentous amount of early work that was done to develop the propellant itself and to bring it to its first on-orbit demonstration under GPIM. Those are some of my colleagues who have been at AFRL for many years. But GPIM's success, so that was the Green Propellant Infusion mission, lasted about a year and just completed its mission last August. And that was the first on-orbit demonstration. And so really for my work, focusing more on let's get all these thrusters, this technology graduated to the mass market, basically.
So it's great that we've been talking about ASCENT here for a little bit and talking about the first mission it actually got to perform successfully. So the first test. What does the future of satellite propulsion look like with ASCENT? Why is it so important to use this propellant?
Sure. So this propellant offers a lot of great things. And what it does is it says we can do greater specific impulse, which is basically your gas mileage in space. saying how much performance can we get for a certain amount of propellant. And then it also has an increased density over the current state-of-the-art hydrazine. And so what that provides is either you can increase your satellite lifetime, or you can instead say, I'll just launch more payload to orbit. And then finally, also as far as propellant loading, there's an operation known as escape. And with that, escape means self-contained atmospheric ensemble. Very good term there, fancy term. But basically, and you can, again, Google this one because it's an interesting one to look at, actually, when you look at what's involved. Because typically with the propellants that we use, they have what we call high vapor pressure. So effectively, you can smell them really easily. So it'd be like, when you think about vinegar or ammonia, it has a very strong scent. In this case, those are considered, the strong scents that you would smell in these cases are actually toxic to some extent, and they're grades of toxicity, right? But the difference with a scent is that it has a low vapor pressure, but it's also, the green terminology also comes from the fact that it's not considered toxic or carcinogenic, really. And so with that, instead of having to wear a full escape suit, you can now wear the typical clean room attire for loading, which isn't very much to say at all compared to even, a larger class clean room. So you're not even in a full bunny suit necessarily, or clean room suit. Sorry, it's terminology there. And with that, you have, just immense cost savings because you don't have, and time savings. You don't have to have everybody fully certified for things in terms of escape. The operations can go a lot more smoothly. And then with the basically lower vapor pressure, it also offers you the opportunity to say, okay, well, I can load this, and I don't have to. If we had a delay in launch or something came up, I don't necessarily have to monitor it as closely as I would other propellants because it'll just be very stable, which is a very nice characteristic. Those are kind of the main three areas that we want to focus on. But the improved specific impulse performance and density really lend itself to opening up a whole new regime of how we look at spacecraft travel, spacecraft flight.
There's an aspect there that honestly I never considered, because I understand that making this more effective, obviously for flight, so better gas mileage, as you put it, and opening this up to the market would be great to help for commercial space flight. But what I never considered was actually making this safer for people putting fuel on board the spacecraft. Like that's an aspect of I guess just the process I didn't think that we would ever, at least at this point, find a solution around. But that's so cool to see that, like you said, it makes it easier for people to actually handle this fuel as well. That's just, it's wild to me.
Mm-hmm. Yeah, no, it's been very much a game changer. And there's certainly other green propellants out there. This isn't the only one. But certainly for the performance improvements it has, we think it's very promising.
And one of the very cool things that you touched on earlier as well, and that we had a discussion about, was working on a lot of these different projects when you're at JPL. And something that kind of was interesting to me was that when you guys were working on these thrusters, you were able to pull a lot of these from the market or had commercial access to them. But when you transitioned to AFRL, you guys had to start designing or really working from scratch. So can you talk about what that was like for you and how maybe your approach to projects has changed, having to build from the ground up instead of having access to a lot of these parts beforehand?
Sure. So you definitely need to reframe your thinking and to some extent your expectations and timing and schedule. So going from basically a flight environment where you get on contract and you're going to go buy X thing and you're going to get it in X time and then integrate it and it's going to have a standard specified performance, to an area where you have more tenuous timelines. It also, though, allows more room for creativity and opens up a plethora of great challenges to go and tackle with the community. And I think that's where I really enjoy it, is that there's just so many things to go off and tackle at this juncture that it really allows to go and pursue certain interests or work on certain improvements in different areas, and really opens up the ability to think creatively about how to go tackle a lot of those challenges.
Yeah, how interesting is that? The fact that, like you mentioned, there's a lot of these things that you knew the benchmarks and knew what you were getting and pulling in the parts that you knew could get the job done. But now you're like, well, we know what we should reach. How are we going to get there? It's cool to have that creative aspect. Like, I love having some of that freedom in mind. So that has to, like you mentioned, has to be very cool.
Mm-hmm. No, it's very enjoyable.
And I'm glad you talked about timing, because a lot of what we've talked about today really ties to, well, in the realm of space takes time. So what is something that you do, or at least in terms of how you approach these things, what is it like knowing that, like you mentioned, Mars missions, or even sending out like a Cassini probe, like that's going to take years or even decades? Like, what is it like knowing that something you touched may not see its full mission completed for a long, long time?
One of my good mentors at JPL always pointed to that as well, and pointing out that working space travel is difficult. It requires a lot of patience and resilience because you may only work on 4 major programs in your lifetime, depending on the pace of how space travel goes. And consistently in the last, I guess, 50, other than the space race, but in more recent years, we definitely have some big programs, and they're large programs, but as you were saying, they definitely take time to build, integrate, complete, launch, and then still reach their destination. And then after you get the destination, there's all the operations, right? So look at Cassini, it just wrapped up in the last half of the 2010s, but it launched in 1997. And before that, they were building it. So when you look at those, you may have, if you wanted to go from cradle to grave on some of these programs, it could be half your career. And in some ways, some people are very fortunate in that they love to follow those larger programs from cradle to grave and have been a part of everything for that long. On the other hand, in the R&D environment, it's very different because you're saying, okay, well, you are now on a much, much faster pace, much faster timeline. But in both cases, I think both require a great deal of patience and resilience. But at the end of the day, it all pays off when you have mission success due to the hard work you and your team put in. That's the key, and that's the takeaway. So whether the timeline is 10 years or 10 months or somewhere in between, and there's little gains, right? There's not always necessarily the big fanfare results that you see on TV or through the media. There's all the little things that happen in the lab that are successes that only get put into a paper that a certain part of the community will read. But all those little building blocks add up to those major days where you have those amazing successes. And that's the takeaway. And that's why most of us keep coming back for more, right? Because some people would say those timelines are so long. I could go working, on the new iPhone and iterate every year and have a new product and make those developments. And those are great things too. Certainly aerospace takes and specifically space work, spacecraft work, space flight work, takes a certain type of person, because you definitely have to have the patience and the desire to see those small incremental changes, but also those big mission successes occur.
Absolutely. Even thinking about the work that you're doing now with ASCENT, I mean, that's been going on for a couple of decades from, the basic research that, got us to that propellant. So you're working on top of the work that someone else is invested, most of their career in.
Absolutely. Yeah. So those timelines all come together. And so it definitely takes all different types of people and all different types of backgrounds to make propellant work, a spacecraft work, all of those things. And you build off of those who've gone before you, and you're making new work for those who come after you. And I enjoy working with interns and all of those things every summer to try to make sure that we open up those opportunities to them or make them aware of what's going on, because propulsion is very much a tight community and a small community. And so it's not always the easiest thing to, as a university student, get involved in propulsion, because there are so many different, hazards and such that a lot of professors aren't necessarily willing to sign up to, let's go build a rocket engine or test a thruster. And all of the things related to propulsion are costly. And so when you look at, you can go buy a Raspberry Pi or a different controller and go play with electronics, propulsion just doesn't lend itself to the same kind of pick it up and go do necessarily at the levels that we test at for certain. And so it's always key to me to try to bring that next generation into the fold as well, to say, okay, these are the great things that propulsion offers, and something you should at least look into.
Yeah, I think that's a really good bow on this package of our podcast here, talking about you're standing on the shoulders of giants with your work. I mean, we started this conversation off with talking about Goddard and, and now here you are talking about we need to invest in the next generation, because they're the ones that are going to carry out the ultimate work that you're doing today.
Yes, absolutely.
Well, thanks for joining us.
Yeah, you're welcome. It was a pleasure.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.